Okay, so in section 3.1, we're looking at quadratic functions and applications. And the first thing that you need to notice is that there are two different forms that a quadratic function can present itself. For example, the standard form here looks like the type of equation that you and I were working on prior to this chapter, where they were asking us to solve the quadratic equation. Now we write this as a function, where remember f of x is just another way to write the variable y. And so now it allows us to go and graph the actual function itself. We also have a different form of the quadratic function, and it's called the vertex form. The vertex form looks a little more familiar to us because this actually looks like someone is talking about the transformations. Back from our past, we know that in transformations, the h value here would tell us if we were going to have a horizontal transformation. And so it would tell us we are going to go to the left or to the right, moving our points, that is, for each point in the graph. And then the k value here was what we referred to as the vertical translation. And this is the one that would tell you if it went up or if it went down. The actual picture, if it would scoot all the way up or if it would scoot down for some reason. Another part that you and I have already seen before would be this leading coefficient, is what we called it. In both forms here, we have the letter A. This A is still the leading coefficient. His job is to tell us whether or not, in the past anyway, this was what we called the vertical stretch or the vertical shrink. Also, this number sometimes was positive or it was negative. And so we'll see today what the positive A value does to the graph and what the negative A value does to the graph. The next few things here that we're going to talk about are more like characteristics of the quadratic function. And when you go to the graph of a quadratic function, it automatically will look like a parabola. So quadratic functions always look like parabolas. And in a parabola, if you're a function, you're either decreasing and then changing your direction to increase through like a curve, or you're coming from increase and going to go through a curve, and then you're going to do a decrease. Since there's only one place where the direction can change in a quadratic, there's one point that's special to us, and that point is called the vertex. And the vertex, you'll notice here, is a point, and that point is h comma k. H comma k. Now what's nice about the vertex form of the function, you'll notice that this h and k that they speak of being what they call the vertex, those values are already showing up for us in the vertex form of the quadratic formula. Whereas if you look at the standard form of the quadratic function, you'll notice that there's not an h or a k value in the problem that is obvious. So in one case, the vertex form, the vertex will be easy to find. In standard form, the vertex will be something we calculate, and we'll show that a little bit later. Let's go back to this value of a. And we said if you have the value of a, and this value happens to be larger than 0, so that means that it's a positive number. What it tells me is that the parabola is going to open up, and it also then gives us a vertex that is going to be classified as a minimum point. So if you'll come down and look at this first picture on the left-hand side, you'll see here that this is where I'm looking right now. You will see that the parabola is facing upward. The reason why it's facing upward is because the A value is greater than 0, it says. You'll also notice that there's a point where the curve changes direction. That is called the vertex. Sometimes you'll have people come in here and they'll put like the letter B right there, so everybody knows that's the vertex. Regardless, the vertex is always going to be the ordered pair H, K. Another thing that you'll notice is that in both of these graphs, you'll notice this dotted line that's going up and down. And what this is what they call the axis of symmetry. So with the axis of symmetry, you'll notice that it happens to be an equation of a line, and actually it's a vertical line. If you go back to what we know about vertical lines, a vertical line, first of all, was not a function itself, but we describe a vertical line as x equals, and the vertical line, because it always goes through the vertex right here, this would actually be x is equal to the h value in the vertex. So when you find the vertex hk, you've also identified the vertical line, which is going to act as the line of symmetry, or what we call the axis of symmetry in our textbook. Be sure that you always write it as an equation. A lot of people will forget and they'll just put down the number for h, and that is incorrect. Let me go back up here real quick and let's talk about what happens if a is going to be less than 0. That means that a is now negative. That means that the parabola has now faced downward. And now we happen to have what they call a maximum point. A maximum point. So if you look at the second version here that we could possibly have in the green box here, you'll notice that it kind of has exactly the same features. This time the parabola is going upside down, and the reason why it's going upside down is because of this value here of a. A happens to be less than 0. So that's why this graph went upside down. It still has a vertex. And that vertex is still right there, the point at which the increase changes to decrease. And so that's going to be represented by the point HK. And once again, we have an axis of symmetry that comes right through the vertex. The fact that it's going, that the parabola is facing upward or downward is irrelevant. The vertical line that acts as the axis of symmetry for us is still an h equals, the x is equal to h. Okay, x is equal to h. So there's quite a few things that we can find from a picture. We can find the vertex, that's one thing. The second thing, we can find the axis of symmetry. The third thing, we can tell you why that graph is going up or down. And the fourth thing that we can tell you about is what they referred to in the last chapter as the maximum or minimum value. In that chapter, they were asking us about the relative max or min, but what's unique about the quadratic function is that it will have one minimum or one maximum, and that's all. So you'll notice in the notes written above there, it tells us that if for some reason you have a parabola that is facing upward, then you will have a minimum value, and that minimum value is K. This is the first example in the red or the pinkish kind of colored box. If you and I are looking at a graph that faces downward, then the maximum value of the function is K. So the Y component of each one of our vertices happens to be right there. That happens to be either the max value or it's going to be the min value. Okay. So the vertex gives us a lot of information. You'll see right here that the vertical line acting as the axis of symmetry is right in there. You'll see that the max or min value is the K value. And so it tells us a lot of information. So in this first example here, they want us to find out, they want us to tell them, do you think that the function is going to open upward or downward? Then identify the vertex and then determine the axis of symmetry. At any time at all, you are more than welcome to go and graph this in the calculator. If we go to the calculator, we would use our Y1. We would type in exactly what it says, the way it says it, and then we could go graph it. If we graph this, then one thing that we'll see, we already know that it's quadratic because it has a high power of 2. The parent function here happens to be y equals x squared. And then we also see that we have some transformations taking place right here. Now, all the points are going to move 1 to the right and 2 down. And so if I'm looking at what I know about transformations, or if I'm looking at my graph on the calculator, I already know that I'm going to have a vertex move to right there. I can also tell people, let me write those down real quick. My vertex is 1, -2. I know immediately that my axis of symmetry is going to be the vertical line. X is equal to whatever the x component of the vertex is, and that's the number y, or that's the number 1. I can come in here and lightly dash that through our vertex. Here's the axis of symmetry. The reason it's dashed is because it's actually not part of the function itself, but it is a nice guide for us. And then I can go to my calculator and I can get some other points that actually lie on this graph. Now, if you remember a little bit about quadratics, you can kind of figure out what's going to happen. We actually have a value here in front. The A value is a 3. And they said if A is bigger than 0, then the graph is going to face upward. So I already know that the graph is going to go up. I know that the vertex is 1, -2. And I know the axis of symmetry is x is equal to 1. If I want to go and find some more points here on the graph, like I said, if you remember a little bit about how the stretcher will work, you can go ahead and do that. If you don't remember how the stretcher is going to work, then by all means go to your graphing calculator and get you some points. This is going to get pretty big pretty fast. Here what I did was this point away from the origin normally would have been 1 over 1 up. It's now 1 over and 3 up. The next point would have been naturally 2 over 4 up, and now it's going to be 2 over 12 up. So it's going to be up in here somewhere. And so what I know about my graph then, let me make my vertex a little bit bigger here, okay? And I know then that my parabola is going to look something like this. The neat thing about the axis of symmetry is that if there's a point that is over to the right of it, then for the same amount of distance, you're going to have one on the left side of the axis of symmetry. Okay, I would use my calculator to kind of get an idea of what the picture looks like. I would use my table of values even to kind of help me plot some more points. All right, so that's what that problem is asking us to do there. Here's another one. In this case, this example here, you'll notice at the very beginning, it tells you that A is going to be -1. Now, they didn't write it that way because we don't have to, but if you think about it, this is actually y equals -1 times x plus 2 squared plus 4. This is definitely vertex form because I can see the transformations taking place. First thing, let's see what they ask us. They say, part A, determine whether the graph of the parabola opens upward or downward. Remember what allows us to make that decision. We always look at the value of A. In our case, A is a -1. That means that A is less than 0. And according to our information on page 1, this will force the graph to go upside down, or what we call downward. The second question here asks us to figure out what the vertex is. And remember what the vertex form of the equation looks like. It's y equals A times x minus h squared plus k. That's the vertex form. And so if we kind of look at how things are working up here, we've trained ourselves already for transformations that says if inside the parentheses of the parent function you see +2, then what that tells us actually is this was 2 to the left. And so if you go and move a point 2 to the left, you know that you're going to have a -2 as your x component. And the back end here, this +4, always told us about the vertical translation. And this says you're going to go up 4. So that translates to a +4. So this is our h is -2 and our k is 4. If you look down here near the bottom of the page, it asks us to determine the x-axis, the axis of symmetry. And like I said, once you identify the vertex, you can actually identify the axis of symmetry, and you're all ready for either the max or min value. We can answer both of those immediately. So first off, the axis of symmetry. The axis of symmetry is always going to be a vertical line, and vertical line equations are x equal, and it will run through the x part of the vertex. This is our vertex right here. They use the call letters h and k so that we can recognize those are actually transformations taking place. But this would be x is equal to -2. To determine if this is going to be a max or min value, up above here, our value of A told us that the graph was going to go upside down. So right here, our vertex, this would look like a maximum value because it's at the top of the picture. So I already know I'm going to have a maximum. Its value, since this is the vertex at -2, 4, the k value or the function value is always the second component. So we know that we're going to have a maximum value And that maximum value is going to equal to the number 4. If they had asked us what is your maximum point, then we would have written -2, 4. Now again, at any time, you and I could have taken our function, gone to our graphing calculator, typed in our y1, as negative group of x plus 2 squared plus 4. So at any time, you can also go and graph that. To determine the x-intercepts, this format here, basically, you just have to go through and solve it. So to find any x-intercepts of any function or equation, we will let the y equal to 0. If we do that in this equation, this would say the negative of x plus 2 squared plus 4 is equal to 0. Now solve for x, and that'll indicate our x-intercepts. Now, if you've already sketched your graph, you might be able to go to the graphing calculator, look at the picture, and kind of identify these x-intercepts, but we'll still want you to algebraically figure that out too for us. So let's go back up to the problem that we were given. A lot of times when people see a group that's been squared, they want to FOIL that out. Let me share with you an alternative type way of solving this. If I were to add this group of x plus 2 squared to both sides, I would end up with 4 equals the group of x plus 2 squared. And what happened is I just added that group squared to both sides. Now I have a perfect square. X plus 2 squared is equal to 4. So if I come in here and I take the square root of 4, remember 2 answers are going to form. And if you take the square root of a square, then you end up with x plus 2. On the left side, the square root of 4. 4 is a perfect square, so that's plus or minus 2. And now we can go and see what this delivers to us. We know that x plus 2 is equal to 2 would be one of our equations for the x-intercept. So this allows us to know if we subtract 2 from both sides, x is 0. The other one that we have is x plus 2 is equal to -2. And when I subtract 2 from both sides, I actually get x is equal to -4. So I have 2 x-intercepts. One of them is 0, 0, and the other one is -4, 0. Be sure that you write these down correctly. In your Connect Math, if they ask you what is the x-intercept and they don't indicate that they want it as a point, then you'll just put the number 0 and the number -4. Those are your 2 x-intercepts. I prefer that you write them as points. So this is what I want to see right here from you. The next one is to determine the y-intercept, and to find the y-intercept, the mathematics usually is a lot quicker, because to do that, we always let the x equal to 0. And so if you go back to the original problem, it said that y is equal to, sorry about that, y is negative group of 0 plus 2 squared plus 4. And if you do the arithmetic here, 2 squared is 4, and you'll end up with a -4 plus 4, so y is 0. So our y-intercept is 0, 0. Now this is one thing that's unique. If you ever find out that one of your x-intercepts is 0, 0, then the y-intercept is automatically 0, 0 also. It's the only point that can actually play both x-intercept and y-intercept. If you look at your picture on your calculator, you'll see that your graph is actually going through 0, 0. So that we can have a small sketch here of what we have going on, let me get a set of axes drawn. This tells me here that I have a graph that is have a vertex at -2, 4. So if I move over to -2 and make this value 4, there's my vertex. My axis of symmetry will be coming right through that vertex. Let me mark the vertex for us. We also know that it's going to head downward. And because understood in front of this grouping here, that's really a -1 right there. All it's going to do is just take its original shape and flip it over. Again, please use your graphing calculator for the table of values if you need to. And what this tells me is that I'm going to end up with over 1, down 1, over 2, down 4. And so, like I said, this is why we kind of like this cool idea about symmetry. If this was 1 to the right and down 1, then that's 1 to the left and down 1. 2 to the right, down 4, so 2 to the left, down 4 would be on there. And so our graph will look something like this. Okay. Now, one of the last things they ask us about is what is your domain and range in interval form? And when we look at this, the domain of a quadratic function is an automatic. So if we come in here and we want to see what the domain is going to be of this graph, basically you're just asking yourself what x's will it use? Well, the domain of this graph, and actually any quadratic function, is -infinity to infinity. It's all real numbers. It's a smooth and continuous graph, and it used every single x in order to get that picture drawn. As for its range, don't forget, is always low to high. So when we look at this picture, these arrows are indicating that they're coming from -infinity. The range is the y-axis, so we're using all of these points. As I climb up the y-axis, the graph stops right there. That was the number 4. So I know from -infinity, that's the low, up to the number 4. I have to use a square bracket here because there's actually a point at 0, 4. Okay. Or my bad, -2, 4. So that's the highest value it uses in the y direction. So when we talk about analyzing a graph, this is what we're talking about. What are the different characteristics of your graph? How did you get them? How do they work together? How does one thing help something else out? And basically the big identifiers here are, number 1, the high power was 2, so I know it's a parabola. The next thing was I could read off with not much trouble what the vertex was going to be, so I knew the transformations. I could also look in front of the parentheses and decide if this graph was going to go up or down. All right, so let's look at our next problem. And here things are going to change just a little bit. We see that the quadratic function is now going to be written in what they call standard form. Standard form. When you look at the standard form and they ask us to find the vertex, it's not very obvious anymore what the vertex is because you don't see the letters H and K in here. You don't see them in that problem. So what we have to do then instead is we have to actually calculate it. Now, once again, you can use your graphing calculator, go graph it, identify where you think that the vertex is, and then go and verify it through your algebra. So let's say that we're going to look at this function here. Since all of my terms are over on one side, that's what's so beautiful about a function being written. I already know that my a value is a -1. I know that my b value is a -4, and my c value is -7. Kind of like if we were going to solve this quadratic to find its solutions. We were finding a, b, and c for the quadratic formula. Well, actually, we only need a and b, okay? And so for the vertex, if we're looking for the vertex, we've already been introduced to him as hk. I don't have an h or k, meaning I don't know what the transformations are because it's not written in vertex form. So I'll have to calculate them. The vertex, since again it's called hk, to find the value of h, you'll take the opposite of your b and divide it by 2 times a. So we'll have the opposite of -4 over 2 times -1, and that becomes 4 over -2, which is -2. So right now I know that my vertex is going to be -2 comma something. Now the way that you find what the function's value is going to be here, the k value asks you to go to the function and plug in the number that you just got for h. See that I'm just going to plug him in right there. So when I go back to the function started off -x², so that's where I'll put -2. Then it says -4 times x, that's where I'll put another -2. And I apologize, I'm running out of room. Let me put -7 there. So when I come in here and I try to figure out what k is actually equal to, I can do the arithmetic on my calculator, or I can do it by hand. I know this is going to be a -4. This will be plus an 8. This will be minus a 7. And so when we do the arithmetic, this gives me -3. So my vertex, that's the k value for the vertex. My vertex is -2, -3. That's the vertex. So standard form doesn't give us a very quick way to find the vertex, but it does still give us a quick way to figure out if the graph is going to go up or down. If you look at the a value, our a value here was a -1. That's what was right in front of the x² term, the leader. And since a is less than 0, a was -1, that's less than 0. That means that our graph is going to have to face downward. It's going to be downward. The vertex we just identified, I didn't write it in the correct place, it doesn't look like. So the vertex here is -2, -3. Remember, once you find the vertex, you can immediately, doesn't look like it printed for some reason. This part G down here should have said find axis of symmetry. And the axis of symmetry is going to be x is equal to, so this will help me find that. X is equal to -2 because that's the x part of the vertex. On this problem, they didn't ask us if we have a max or a min value, but if they had, because of our picture turning downward, you would definitely have a vertex that would be sitting on top of, which indicates to us that we have a maximum now. And that maximum happens at the vertex. And so we would have had a max value of -3. They didn't ask it, but that's what would have happened. It says determine the x-intercepts. And I just realized that the problem had changed, didn't it? Okay. Well, that's the information we would have had. Let me backtrack a minute. Sorry about that. I'm so used to doing everything at once. Our first example only asked us for the vertex. This second example here is actually asking us to use a different equation. So let me back up then. Okay, so in this problem, they're asking us to actually find all of the different characteristics or analyze the entire graph. And so again, here we have an A value, which is 2. And since that A value is bigger than 0, we do know we're going to have a graph that will face upward. So we will have a graph that faces upward. They're asking us to determine the vertex. You can definitely go and graph it on your calculator if you'd like to. For the vertex, to identify it, to make sure that we know algebraically how it's calculated, we've already been told that A is 2. The B value is -10. And since this equation is in standard form, we'll have to go and calculate our vertex. H is equal to the opposite of B over 2A. This is the opposite of a -10 over 2 times 2. This is 10 over 4, which is actually 5 over 2. Now, we really don't want to go into decimals if we don't have to. And especially sometimes these decimals will not end. They're going to be non-repeaters. And so let's keep all of our values as fractions unless we're told otherwise. So what I know about my vertex already then is that it's going to happen when x is 5 over 2. And now for the k value, I'm going to go back to my function. I'm going to load in the fraction 5/2 everywhere x is. And now do the calculation. So this would be one of those that would be really good to use a calculator on. And so if you go and type that into your calculator, that's what I'm going to do too. Make sure that you type in everything according to how it's written. Let me get mine done. And then verify with me if you end up with my calculator says -17.5. What I'm going to ask it to do is go to the math, number 1, which is a fraction, and turn that into a fraction for me. So -35 over 2 would be the actual fraction value. So my vertex is something that would be a little bit harder to read. You probably thought that your calculator wouldn't show you where the vertex is because it's so deep. Now that we know where the vertex is, this problem here did not ask you about axis of symmetry, but the axis of symmetry, if we had been asked for this problem, your axis of symmetry would have been x is equal to 5 over 2. Because this graph is going upward, if we had been asked, this would have had a minimum value, and that would have happened at -35 over 2 because that's the k value. It asks us to find the x-intercepts, and so now if we go and find the x-intercepts, this is when we let y equal 0. So we'll set this equation to equal to 0. And we will solve this for x. Once we find the 2 values for x, that'll tell us where the graph is going to cross the x-axis. I don't believe this thing will factor, doesn't look like it will. And so our only objective now, when we go in here and solve, since it is quadratic, I'm going to have to use the quadratic formula. So I'm going to use x is equal to the opposite of the b value plus or minus the square root b squared minus 4 times a times c, be careful of signs, all over 2a. So this is why we learned how to solve a quadratic equation before we went into actually looking at their function. If you'll do the arithmetic, kind of how I showed you in the last chapter, I can do the 10 by myself, I can do the 4 by myself, and let's see what goes underneath that root. So it looks like we're going to have negative 10 squared is 100, and it looks like we're going to have plus 40. So it looks like we're going to have 140 underneath the root. The first thing we'd have to do now is to go in there and simplify what is the square root of 140, where we would pull out pairs of factors. What I know about 140, this is 10 times 14. I could start there if I wanted to. That's 2 and 5. That's a 2 and a 7. So I definitely have a pair of 2's. So this fraction becomes 10 plus or minus 2 square roots of 35, because I have a 5 and a 7 still left underneath. This is all over 4. And now, in order for you to simplify a fraction like this, it has 2 what we call outside numbers, and the denominator must all share something in common. They're all divisible by 2. So if I divide 10 by 2, I'll find out that, let me come over here in this area. I will find out that x is equal to 5 plus or minus. If I divide the 2 by 2, it's a 1. Well, I don't have to write the 1 because 1 times the square root of 35 is just still the square root of 35. And if I divide the number 4 in the denominator by 2, I get 2. So if you go to your graphing calculator and you try to look to see where the x-intercepts are, they're there, but it's not going to be something you can read, unfortunately. Our x-intercepts, one of them is 5 plus the square root of 35 over 2, comma 0. And the other one is 5 minus the square root of 35 all over 2, comma 0. Your calculator will allow you to plug that value in if you go to trace, and you trace 5 plus the square root of 35 over 2. It should give you 0 on the graph for the y value. For the y-intercept, this tells us to always let x equal to 0. And so if we let the x equal to 0, then we'll find out that the y is equal to 2 times 0 squared minus 10 times 0 minus 5. Now, when you do this arithmetic, you'll find out you get negative 5. This is probably one of the only things that standard form gives up immediately. If you look in the original problem up here, you'll see that minus 5 is back here at the back. That looked like I just tore over it. Hold on. You'll notice that the negative 5 is back here in the back. And what we find out is that if you're in standard form, the value of c, in our case negative 5, ends up being the y-intercept. But this is only true if you're in standard form. So if we go back and want to write up our y-intercept, sorry about that. Our y-intercept is actually going to be 0, -5. Now that one you probably can read on your calculator pretty well. For the domain and range, we know that the domain of any parabola is all real numbers. To find its range, you definitely want to look at its picture. Okay, you want to look at its picture. And what we find out, if we go back to all of our clues, the first thing we know is that the graph is going to go upward. We also know that it's going to have a vertex that's 5/2 is about 2.5, and -35/2 is about -17/2. So right about down here, -35/2 over 2.5 would be right about there. There's the vertex. And then as you go through, we find out that, let me get that point back up there. And we can go through the graph. And now you can see that the range here has a low point of -35/2. We'll use a square bracket to hold it. And the arrows are implying that the graph keeps growing to infinity. And so that would be your range. So the reason for indicating all of these different characteristics or analyzing the quadratic function is so that you and I can come in here and put this as a model of certain things. Things that have parabolic arches to them, for example, this one says throwing a football. So when you throw a football, as much as you may think maybe it just goes straight across, it really doesn't. Think about a quarterback throwing a Hail Mary pass to the end zone. It's going to have a natural arch, and that arch is going to go something like this, okay? If you shoot arrows, even though you may think you're shooting straight across, it's going to have either a natural lift to it, or it might actually have a under lift to it like that. Regardless of the fact, it's definitely going to make some type of arch, okay? So in our problem here, it says the quarterback throws a football with an initial velocity of 72 feet per second. The height in feet of the ball can be multiplied by. So this h right here, according to the words, tells me this is the height of the ball. And if you read on, it says where t is the time in seconds. So this is the height of the ball at t seconds. That's what h of t means. What's nice about having this formula already written for us, it's taken into account gravity, it's taken into account like where he's thrown it from. We're just going to trust that the physicist actually has this correct for us. And now we're just going to go and answer some questions for him. It says determine the time at which the ball will be at its, and here's one of our words, maximum height. Determine the time at which the ball will be at its maximum height. Well, we know that maximums only occur if the graph faces upside down. So my question would be, do we have this type of graph or not? You can definitely go graph it on your calculator. You'll have to play around with your window a little bit, but you and I know it's going to go upside down because look at the a value. This a value here is -16. And so if you're talking about, if you're talking here about a being negative, then that means a is less than 0. So of course the graph is going to face downward. So I do believe we're going to be able to find a maximum height. Now earlier when we were talking about maximum height, this is our max up here. What you and I have to now go back and do is look at the way this function was written. This is written h of t. We're used to seeing things like f of x, where x is the input. So in our case, t is playing the role of x. So t is input. I'll put out here the old-timey x value. And then h is actually playing the role of f. Well, f of x was actually a y. So h is your output, which is the old-timey y value. Now, the reason I'm doing this is so that whenever we talk about this graph in just a minute, or possibly you've already graphed it on your calculator, when I look at this thing and I put the x and y axes up with it, the x-axis here is now known as t for time, and the y-axis that you and I used to call that one is now known as the h. This means that every time we go and look at points that are on this curve, the only point I'm going to be interested in right now is what is the vertex. This means that all points are now going to be, instead of x, y, like we're used to, it's now going to be t and then h, t and then h. So this question says, determine the time at which the ball will be at its maximum height. Determine the time. So you're trying to figure out the t value. So we can go to our function here, and we can notice that this is in standard form. So we've been given that a is -16, b is 30.4, and so to find what used to be called the h for the vertex and the k for the vertex, we now are looking for what is time, what is t. So t is going to equal to our -b/2a. That's going to be the opposite of 30.4, all over 2 times -16. And our t value then, if you go to your calculator, looks like we may have to throw this back as a decimal. In our instruction here, they did not tell us like how to round it, but you can bet I always will. -30.4 divided by 2 times -16, that'd be -32. And I got a value of 0.95. Running back up to the problem, I know that t is measured in seconds. So 0.95 seconds. This is going to be my value for how long it takes for the ball to reach its maximum height. Traditionally, they almost always ask you now the second part of the vertex. And in this case here, they did us right by saying, what's your maximum height of the ball? So in this case here, I'm actually now solving for h, which is height of the ball. So when I go back and I look to see where height was for the ordered pair and follow it back, it used to be called y, that's the k value, position for the vertex. So to find the k value, which is going to be for our height, I would go back to the function, height at 0.95. And everywhere t used to be, I'll now put in 0.95. Once you plug that value in, now go use your calculator. And let's see, how high was the ball when the quarterback threw it when it was at its highest? And I got 19.44. I need to run back up to the reading of my problem here and find out what was the unit for height. Right there, it tells me the height is in feet. So I can go back to my answer here. And I have 19.44 feet is how high the ball was at its maximum. So basically, in their own little way, they were really asking me, where's your vertex? It's just we have to translate, since this is an applied problem to a real situation, what does vertex mean? Well, in our case, it meant time, comma, height. In the last part of this problem here, it says determine the amount of time required for the ball to reach the receiver's hand. If the receiver catches the ball at a point 3 feet off the ground. I don't believe that this word at belongs right here. Let's see if that reads better. Determine the amount of time required for the ball to reach the receiver's hand if the receiver catches the ball at a point 3 feet above the ground. 3 feet above the ground. So let's go back and look at our picture. It's definitely not to scale by any means, but right here we said that this number was 19.44 feet. It happened at 0.95 seconds, and they're wanting to know when will how long, determine the amount of time required for the ball to reach the receiver's hand. Well, here's the quarterback, right? He's at the beginning. The receiver is going to be over here, and he's at 3 feet. He's at this level at 3 feet right there. So what you and I need to do then is we need to go back to our problem. Let me write it down. H of t was equal to negative 16 t squared plus 30.4 t plus 5. And this time, what we need to do is we know that our receiver, okay, the height of the ball when the receiver grabs it is 3 feet off the ground. So I know that this equation has to equal to the number 3. This is a quadratic equation. We are going to get 2 answers. You and I are going to have to figure out which one of those 2 answers makes sense for the receiver. Now, I'm not going to attempt to try to factor this thing. Regardless, I know that this side needs to equal to 0, so let me subtract 3 from both sides. That 3 will subtract from the 5, and that'll give me a 2. And now I need to go solve for t. One of the ways to solve this is to factor it. Like I said, I'm not even going to give it a shot because I've got a decimal number in there with 2 non-decimal numbers. It probably is going to be a lot harder for me to try to do. A lot of times in these problems, it'll even say determine the amount of time to 2 decimal places. It'll even kind of like insinuate to use your calculator. So what I'm going to do for solving for t, I'm just going to go to use the quadratic formula. And the quadratic formula says take the opposite of your b plus or minus the square root. You want to square your b minus 4 times a times c. I'm getting really close to the edge here. All over 2a. Now I'm going to go ahead and clean this up just a little bit. But like I said, almost always in a situation like this, they're going to give you an idea that the answer needs to be calculated on the calculator. I have no idea what that is underneath the root. I'll come back and look at it. This is divided by negative 32. All right, so if you'll go to your calculator and figure out what 30.4 squared minus 4 times a negative 16 times a 2. And I ended up with a number 10521.16. That's what's underneath my root. You can see now why, for sure, there was no way to factor this on our end. So what we want to do then is we want to figure out, you can figure out both of these answers, or you can also kind of use some common sense here. One thing I see is that one of the answers, let me put him over here, one of the answers is going to be negative 30.4 plus the square root of 1052.16, all divided by negative 32. And the other answer that I'm going to get is still negative 30.4 minus the square root of 1052.16 all over negative 32. One of these answers is going to end up being negative. One of these is going to end up positive, or we may end up with two positive answers. This is just one of those things we have to look at. So let's look at this first one here. And we're going to go back to our calculator. If you have that fraction key, alpha y equals, this might be a good time to pull that up. And in the numerator, you want negative 30.4 plus the square root of 1052.16. Down in the denominator, you want negative 32. This gives us a negative time, negative 0.063, and it doesn't stop. And I have an issue with this answer here. How can time be negative? It can't. So this is what we call an extraneous solution. This solution does not make sense. So we're hopeful that the next one will. And so if you go in there and type the next one in, some of you know how to go in there and up in your calculator and grab that last fraction that you just did, re-enter it into your calculator and change the plus to a minus now. If you don't know how to do that, that's okay. Go ahead and just retype the whole thing. But I do get 1.9636, and it keeps on going. So like I said, I sure wish that in the instructions here for this problem, they had said something like round to the nearest tenth of a second, round to the nearest hundredth of a second. Let's say that you and I rounded to the nearest hundredth. Okay, so we're going to take this answer and round 2 decimal places. And so our time then would be 1.96, and this would be in seconds. So in 1.96 seconds, the receiver should have the ball in his hands about 3 feet off the ground. He didn't have to dive for it or anything like that. I mean, it just literally just fell into his arms. His arms were about 3 foot off the ground, and it took less than 2 seconds to get there. The last problem that I have for you here throws people off a whole lot, because what we're about to draw is the geometric figure of what's going on, okay? And then we want to model it if we can actually figure out a model that looks quadratic, so that we can go in there and solve for things like the vertex or the x-intercepts or whatever we need, okay? So let's take the problem and just read what's going on first of all. The first thing he tells me is that I'm going to have exactly 200 feet of fencing. Now, first thing I want to point out to you, when someone says that they have fencing, this means that they're going to build a fence, right? That's what that means. Usually fences are in rectangular form. Sometimes one of the sides will be your house, and then the backyard just has three parts that are actually fenced. We see here in the problem that he tells us that he wants to build 3 adjacent rectangular corrals. That's just trying to make the problem a little bit more difficult. What we're going to do is we're going to go in there and actually divide this rectangle that we've drawn into 3 areas. So now I actually have 3 areas that are connected together. That's what adjacent means. They're all rectangular, so I know that my fencing was drawn in the correct pattern. And now he tells us what we need to go and do. So we've got our idea at least. And he says, I need you to figure out the dimensions that we could use. So when someone says dimensions, and you're talking about rectangle, then the dimensions of a rectangle are length, we'll use L, and width, we'll use W. So before we do anything else, since that's what they want us to figure out, let's go to our fencing over here and let's decide what we have, okay? If you had a traditional rectangle, you would have a length, both on top and bottom. You'd have a width on the 2 sides. Let's look at what we have. In our problem, we actually have a fence that goes across, just like we said, length. And we also have another one that's parallel to it, identical to it. There's another L. When we go to the sides, where normally we use width for the sides, I see here the fence is going to go along this one, so that's W. To make sure that these are 3 separate corrals, there's another fence that's a W. There's another fence that's a W. And likewise, there's another one. Let's go back to our training from basic geometry. When you put up a fence, you are running along the outside edges of a rectangle. So what that tells me is that when someone talks about fencing, they're talking about mathematically perimeter. And the perimeter of this particular item here, we have 2 L's that we could add together, plus we could add 2 W's together, and that's the perimeter formula. Let's go back to our picture. And our perimeter is a little bit different. We still have 2 L's that we can add together. But now we have 1, 2, 3, 4 W, and that will make our perimeter. At the beginning of the problem, we talked about how the fencing deals with the outside edges. The outside edges, in this case, we also have the outside edges of each one of our corrals. And so that's why we had to build 2 more W's in the problem. But this is equal to the fence. So I know that the perimeter has to be 200, and that's equal to 2L plus 4W. All right, let's stop there just for a second, because as I finish the rest of the wording of the second sentence here, it says determine the dimensions. We've already talked about how we're going to use L and W's for dimensions. It should be used to, and here's the key, right here, maximize the area. Maximize the area. So this is what you and I need to be working on. The fact that we went over there and grabbed the perimeter, that's fine. We needed to talk about how does the fence make our corral. But now he says, I need you to go in there and I want you to max your area. Again, let's go back to what we already know. How do we find the area of a rectangle? Again, it looks like this. Usually whenever you're talking about the area of a rectangle, you'll only see 2 dimensions on it because the area of any rectangle can be the length times the width, so LW. They want us to maximize our area. So if I go to the area formula, that's L times W. I have to choose what to do with these variables. A is just going to end up being my area. So that's what I'm trying to maximize. So I'm not going to change this variable here. But A is determined by 2 separate variables. And so one of these 2 variables needs to switch. Either the L has to become a W or the W has to become an L. This is where it gets a little tricky, because this is where you and I now have to go back to what we know about the relationship with L and W for our 3 adjacent corral. What you and I know is this piece of information right here. If I were to decide, since it says find the area of each individual corral and determine what your dimensions are, since it didn't say go find the length or go find the width, I can do whichever one I would rather do. So let's say that I take this equation, I'm going to turn it around, and I'm going to come in here and I'm going to solve for L. So that means that 2L would have to be 200 minus 4W. Dividing both sides by 2, I find out that the length can be written as 100 minus 2 times a W. What I'm setting myself up to do then is to make a substitution. This L will change into a W because L is equal to 100 minus 2W for our corral. Our area formula then, A equals, I'm going to put my L in here. I'll use the same color so you can kind of follow it. That was 100 minus 2W times W. So the only thing that changed in the area formula was how I could speak about the length of the corral based on what I know about the width and the length and 200 feet of fencing. Now I can go in here and look to see what the area formula really looks like. Area, well, this is a W on the back end that's a distributor. So I'm going to take 100 times W. I'm going to take negative 2W times W. And I get 100W minus 2W squared. The problem asks us to find a maximum. When do maximums occur? When the graph goes upside down. Will this graph go upside down? Let's rewrite them in descending order. This is negative 2W squared, positive, so plus 100W. So since A is equal to negative 2, this graph definitely goes upside down. Let's look back at our function now. This is our area. So area is going to be the output. The width is the variable inside the formula, so that's our input. So when we go to find this maximum, That's our vertex. And when we go look at our graph right now, traditionally you and I would have axes here, X and Y. We don't have those anymore. We have to use the variables in our formula. The input, which should have been X's, is actually W. So this is actually going to be the width. I cannot read that for anything, so let me rewrite that as a W. And my height, or my y-axis, should have been the Y. Our Y is being played by A, which is the output. And so this is now area. So points that we find on this graph now are represented by W, comma, A. W, comma, A. Once I know the width, then I can figure out the area. This vertex is where everything is happening. This is where the maximum area will occur, and it'll tell me how wide I need to make my corrals. We know how to find the value, or we know how to find the H and K of a vertex. In our case, our H is being played by W, our K is being played by A. So to find the H, which is actually width now for us, we'll take the opposite of your B value, which is 100, over 2 times A, which is a -2. This width, if you think about how wide is something, your answer has to be positive. It doesn't make sense to have negative width. And so -100 divided by -4, that will give you a +25. Glancing up above there, it did say feet, so I know that my width is going to be 25 feet. To find out what my K value would be for the vertex, that's now known as area. I'm going to go back to my formula. Area was equal to -2 times W, which is 25, we'll square it, plus 100 times 25. And when you do the calculation on your calculator, negative group of 25 squared plus 100 times 25. Hopefully you got 1,875. When you talk about area, we do use the unit feet, but we put a little 2 up here to indicate that this unit of measure, feet squared, is for area. So anytime you talk about the area of something, you have like square yards, square feet. So that little 2 up there on the unit is very important. This vertex gave me 2 answers. And if we go back up to the problem, the first thing that they asked me to do was determine the dimensions, and it's plural. Here's my problem then. I'll put him right here, smack in the middle. I know that my width, I just found it on the vertex, is 25 feet. But what's the length gonna be? Well, lucky for us, down here, when we did that substitution for length, he was waiting this entire time for us to know what W was. And so to find the length, we would use the 100 minus 2 times the width, which was 25. This tells us that the length would have to be 100 minus 50, which is 50 feet. The area I did get from the vertex, and the area that I got was 1875 feet squared. One way to check our work here, we could go to our actual problem, look at the picture, and if we were to allow the L here to be 50, let this L right here be 50, and let each one of the W's be a 25. that gives us 200 feet. 200 feet of fencing. How I got that, I took 25 plus 25 plus 25 plus 25, that's 100, plus 50, that's 150, plus 50 more, that's 200. That's 200 feet of fencing. So I used all of the fencing, and when I use all of the fencing in this arrangement, the best I can get for area is going to be 1,875 feet squared. So the reason why this one's so confusing a lot of times is because when we're talking about building a corral that's rectangular, you look at it and you're drawing a rectangle. But as you start putting perimeter and area together, they end up giving us a quadratic model. And so this quadratic model then allows us to go and find the vertex, the maximum or the minimum, whatever the case is. And so it's a really cool application of mathematics to figure out, okay, where should I go and cut the fencing at? Where should I go and dig the fence post at? It's not just the, well, I'll go try. And if it fits, it fits. If it doesn't, it doesn't. So this is an accurate measurement for us, and it tells us exactly what the dimensions are going to be. All right, I hope this helps you. And I will be getting other notes ready for you and get them on Canvas for you very shortly.